Hello, and welcome to the Reactor Room, where we solve professional engineering problems in the chemical discipline. My name is Zachary Brownstein, and in this video, we are going to solve the following problem. Air expands isentropically in a steady flow process from 850 degrees Fahrenheit and 500 psi absolute to 80 psi absolute. Based on the specific heat capacity of air at room temperature, what is most nearly the change in enthalpy? The first item that jumps out at me is that we have air expanding isentropically. This lets me know that we are in a heat cycle and can use the definition of the change in enthalpy, which is the heat capacity at constant pressure times the change in temperature. Thus, we have two terms that we need to evaluate. The heat capacity at constant pressure depends on the material as well as the state of the material. So let's look back at our problem. We see that we can actually assume that the heat capacity can be based on air at room temperature. So looking at the temperature-dependent properties of air, we see that the isobaric heat capacity is about 0.24. Now we have to be careful with our units and be consistent. We are in the imperial system, so we will be using BTUs per pound mass times degrees Rankine, which is the degrees Fahrenheit plus 460 degrees in order to put it on an absolute scale. Great, so now let's find the change in temperature. We know that we have an initial temperature and pressure as well as a final pressure, so let's put that in. Our initial temperature is 850 degrees Fahrenheit. Let's add 460 in order to get our degrees Rankine. This is 1,310 degrees Rankine. Our initial pressure is 500 psi absolute, and our final pressure is 80 psi absolute. If we make the assumption that air is an ideal gas, there are many equations that relate temperature, pressure, and volume in an isentropic process. An example of this can be found in this top left equation. Let's write that down. That's T2 divided by T1 is equal to P2 over P1 raised to the gamma minus 1 over gamma. We know our initial and final properties. Gamma is the specific heat capacity ratio, which is the heat capacity at constant pressure over the heat capacity at constant volume. Looking at the same dependent property chart, we see that the specific heat ratio is 1.4. So we'll put that in. And so now we can just rearrange and plug in our values. It's important to write all this out, so if there is a mistake, we can always check our work. Okay, this is equal to 0.592 times our temperature. So we're going to change our temperature by a factor of about 0.6. This is equivalent to 776 degrees Rankine or 316 degrees Fahrenheit. So now we have everything to solve this problem. Our change in enthalpy is going to be 0.24. Make sure to keep our units consistent. And we have our final temperature, which is 776 degrees Rankine, minus our initial temperature, which is 1,310 degrees Rankine. Plugging this in, we get a value of negative 128 BTU per pound mass because the units of Rankine cancel out. Great, let's go back to the original problem. We see that some of the answers are close together and some are positive and some are negative, so we have to be extra judicious when choosing. Let's see if we can think about this conceptually. We know that air is expanding isentropically. That means that the temperature is going to decrease, which means that the enthalpy is going to be negative. Thus, our answer of negative 130 BTU per pound mass makes sense, and B is the right answer. Thank you, and good luck.